Hello, so welcome to this video. In this video, I will talk about moduli space. So this is my first time attempting a monologue in English in mathematics, so I hope you can bear with my accent. Okay, so what is moduli space? So moduli space, in other words, is just a parameter space. So it parameterizes a collection of objects that you wanted to study. And by considering the collection of objects instead of just a single object, one can get more property out of it. So, as in the title of the video, later we will talk about several examples, and one of them is like how to determine whether the 5 points determines a conic. So, I want to start with a very uh, old classic problem, which is the following: like, uh, given a stick of length 1, so this is a stick of length 1, and then you pick two random points on it, here and here, say for example. So what is the probability that the three uh, subparts of the stick form a triangle? Okay, the points are chosen uniformly. So the way to approach this problem is you consider the parameter space of what the possible places of the points. So consider a square uh, of side length 1. Okay, this can be considered as the parameter space of the set of points. Alright, so for example, let's color this orange, so or red. So the point here correspond to here, to a point there, and the other point, the blue one, correspond to somewhere here. So this configuration correspond to a point here. So this configuration corresponds to a configuration here. Okay, so this square parameterize the whole configuration space. The square parameterize the whole configuration space. Okay, and since each of the points red and blue are chosen uniformly, independently, so the probability of such conditions, uh, so the set of configurations that satisfy the second condition, that is the probability that they form a triangle, can be determined by the area of which the configuration of points where the configuration satisfy the extra condition. Okay, so for instance, like let's consider a point, the red point, with without loss of generality. Let's assume that the red point is like on the less than halfway of the stick. Okay, so consider all configurations that's on the that has that particular red point. So the question is, what are the configurations that allow for them to form a triangle? Okay, if the blue point is chosen less than red, if the blue point is chosen here, then of course we cannot form a triangle, because the sum of the two smaller one is less than the longer one, and that uh, dissatisfy the triangle inequality. Okay, so at least the blue point must be like uh, uh, to the right of the red point. So and if the blue, okay, so consider the halfway point of this stick. If the blue points also lie on the same side of the red point, then the same problem. We cannot guarantee that. We cannot form a triangle because the sum of the two shorter sticks are less than the longer one. Okay, so the similarly the blue point must also lie to the left of this arbitrary side, arbitrary boundary, where the length of the remaining one is equal to the length of this one, to the shorter side from the red point. Okay, if a blue point lies here, then similarly, then the sum of this, sorry, it's not, uh, let's assume this has length t, then the blue point must uh, consider like a very small segment of length half minus t. If the length of if the blue point lies on this interval, on the interval on the right, then we cannot form a triangle. The three parts of the stick doesn't form a triangle. Okay, so the blue points, this what this left us with this interval of length, this one half minus t. So this has interval of length t. Okay, so in other words, the place where the blue points give us a good configuration is at such interval of length half minus. Okay, and this holds for all points smaller than half. And by symmetry, for all points bigger than half, we also have a similar result. Okay, so what does the parameter? So which point on this square that which points in this square that are good? So the answer is like it's something that looks like this. Ah, okay. Okay, so on the left side, we must avoid all the points that are lower than half, and on the right side, we must avoid all the points that are bigger than half. So we get this. All right. Yeah. So the proportion of the area is 1 to 8. So the answer is 2 8. Right. Okay. Equals 1. Okay. So this is an example of what a parameter space can do. So let's go to the main topic of today's title of today's video. What is the So 5 points determine a conic. So what is a conic? A conic is just a set of points that are determined by a quadratic equation in two variables. So it can be written generally of this form. For some real numbers a, b, c, d, e, and f. So what is the parameter space of conics? Notice that for each conic we can associate it to a tuple of 6 integers a, b, c, d, e, and f. Okay, but two integers can determine the same conic if when when they are proportional. That means there exists a constant, say lambda, such that the coefficients are just scaled up by lambda non-zero. Okay. So in other words, the parameter space of conic. So what is the parameter space of conics? So parameter space of conics is just R6 modulo this equivalent equation. Okay. Or in other words, this is the 5 projective space. So what does so when does a conic lie so when does a conic lie so what does it mean for a conic to pass a point? So for a conic to pass a point, we can consider all the instead of just considering one conic that pass 5 points, we turn the uh, settings around so that we now consider all conics that pass through a point. So what does all conics that pass through a point looks like? So consider a point P or T, your favorite point, and consider conics that pass through P. Okay. So a conic that pass through through T, say T1, T2, okay, must satisfy. So if a conic pass through this, that means the equation for C is satisfied by this pair. That means A T1 square plus B T2 square plus C T1 T and so on is equals to 0. Okay, so in other words, the collection of points that pass through this is the collection of points that satisfy this constraint. Okay, but we can consider this as just like a number, and now consider the A, B, C, D, E, and F as the parameter. Okay, so if we do that, we can see that this equation actually determines a hyperplane. Okay. estimate the hyperplane passing through 0. Okay. Now, what does it mean for a conic? So, if I give you 5 points, what does it mean for a conic to be determined by that point? So, 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 given 5 points, T1, T2, T3, T4, T5. Does there exists a conic that passes through all of them? And in general, the answer is yes, because the collection, if such a conic exists, it must lie in the collection of all conics that lies in the of all conics that passes through T1 and conics that passes through T2 and conics that passes through T3 and so on. So that means that we have 5 hyperplanes. So for example, we have 5 hyperplanes, something like that. And we know that in R6 by a standard linear algebra that these 5 hyperplanes in general position, they intersect at the line. So because we have five hyperplanes, intersect at the line. Okay, that means there exists a line here. And this line is the conic that we want. This is the conic that we want. Conic that satisfy T1 until T5. Okay. So this proof furthermore show that given 5 points, that there exists a conic that passes through them. Alright. So this is like a very good example. One can do the same with cubic equation, and in general you need like roughly n choose 2 points to determine a degree n equation. Okay, so for the last example, I want to talk to you. I just want this. This is going to be like a very short introduction. So the moduli space of elliptic curve. Elliptic curve is the hyperbolic manifold. What does it mean? Okay, so we know that an elliptic curve can be written as a C mod lambda for some lattice lambda. Okay. And we can always choose lambda so that it is generated by two by a single complex number which we call omega. Okay, so we can like rotate the lambda so that one of the fundamental basis of the lattice is 1, and the other one is omega for some omega. And so, but the choice of omega, if we have a lattice, the choice of omega is not unique. So this is one. If we have another points that are some or which are of the form a omega plus b, then this also generates the same lattices. So in other words, elliptic curve is parameterized by points, but in with the condition that uh, the 2 points are equal if they are can be written of this form. Okay, that's the first one, and the other one, uh, since the lattice should be also in finite size. Conversely, if we have uh, another point, say, of the form, if like we can scale by w. So, for example, this is generated by 1 and w. So, if we conversely consider 1 over w and 1, this also generates the same lattice, but it's just smaller. So, we don't really care. So, the equivalence here is not complete. We also need to consider this equivalence. All right. And lastly, if we consider conjugation 1 and omega, then 1 and 1 and omega bar, the complex conjugate, also generates the same kind of lattice. So we need to mod out this space again. Okay. So, but one can show that this is isomorphic to H, the upper half plane, and this second condition is also equivalent to the action of SL to Z, where an element of SL to Z, a matrix acts on the upper half plane by the Mobius transformation as usual. And so this is why we often say that uh, the hyperbolic manifold is parameterized by an elliptic curve. So this has additional structure. So a parameterized space a priori is just like a set of stuff, but each spot SL is a more structure. It is a Riemannian. It's a Riemannian manifold, and you can define a metric on it so that it becomes a hyperbolic space. And for example, this is the it has a fundamental domain, so that each point here in the usual diagram, each point here it's representing actually represents a elliptic curve. One can play with this. One can consider functions on it, which are called modular forms, but we will not touch that today. And yeah, and so on. Okay, so lastly, I just want to talk briefly about some other applications of modular space. Yeah, for example, if one interested, one can the very recent application is that one can consider a mathematical object called Stuka, which is defined by Greenfield, called the Greenfield Stuka. And this can be, and one can consider the modular space of this, and it has become a very complicated space, but it has it is a non-finite type space, And by considering the moduli space of it, one can construct a homology theory, and it can reduce the local geometric local lambda. So this is how Laforgue uh, got his field medal, which is a very interesting subject. So moduli space is like a very fundamental tools on how you consider things. Okay, so that's it for this video. Thank you for watching, and I'll see you next time. Goodbye.